Hello, everyone. Today, I am excited to present our work titled Efficient Rationale-based Retrieval on policy distillation from Generative Rerankers based on JEPA. This research addresses a critical gap in retrieval efficiency and accuracy, and it is a collaborative effort by our team. You can find our contact information and the paper link here on the title slide. Let's start with the motivation. Traditional retrieval is mostly fact-based, where we look for semantic similarity between a query and a document. However, there's another category called rationale-based retrieval. Here, the query and document might not look similar on the surface. For example, in emotional support conversations, we need to find the best reply strategy based on a user's emotional state. Or in robotic manipulation, we need to map a natural language instruction to the best subtask. In these cases, simple word matching or semantic similarity just isn't enough. To solve this, we usually look at two types of models. Large language models acting as cross-encoders are great at rationale-based retrieval because they process the query and document together, but they are very slow. On the other hand, bioencoders are fast because they compute document embeddings offline, but they perform poorly here because they rely on surface-level similarity. We propose RABTreaver, the rationale-based retriever. Our goal is to bridge this gap, achieving the high accuracy of a re-ranker with the high speed of standard retriever. To understand why we need a new approach, let's look at the standard bioencoder. In this setup, the query and document are encoded separately. The document parts are computed offline, which is shown in blue. The online computation, shown in cyan, is very lightweight. However, because the encoder doesn't see the document while processing the query, its efficiency is high, but its ability to capture complex relationships is limited. Now compare this to the cross-encoder used in re-ranking. It concatenates the query and document and processes them together. This allows the model to capture deep interactions, which is perfect for rationales. But as you can see, the inference complexity is quadratic relative to the sum of the query and document lengths. This makes it far too slow for large-scale retrieval tasks. Our core idea is to reconstruct the cross-encoding effect using a bioencoder architecture. We encode the document and query separately as usual, but we then introduce a lightweight predictor. This predictor takes those separate embeddings and mimics the cross-encoded version. We use a distribution-based energy function as our main objective and a KL penalty as an auxiliary task to match the retrieval scores. Let's look at the distillation paradigm we use. The teacher is an LLM-based cross-encoder. Crucially, it uses causal encoding where the document is placed before the query. This ensures the query's representation is fully conditioned on the document's context, which is the gold standard for accuracy in these tasks. Our student consists of two separate encoders using the same LLM backbone. The document encoding remains identical to the teacher's. However, since the query is now processed separately, it lacks the document's context. Our challenge is to bridge this gap by transforming the query embedding to match the teacher's contextualized version while keeping the document calculation offline. To do this, we implement a lightweight predictor. This predictor maps the raw query embedding X to the teacher's query embedding Y. We treat the document embedding Z as a latent vector that provides a necessary context for the predictor to make this transformation. The mathematical goal here is to minimize the energy difference between the teacher's embedding and our reconstructed version. Essentially, we are training the student to predict how the teacher would have understood the query if it had seen the document at the same time. We follow a three-stage pipeline. First, we train the teacher re-ranker. Second, we initialize the student's encoders using the teacher's weights and insert our trainable predictor. Finally, we perform distillation by minimizing the energy between embeddings and the KL penalty between their final scores. For the teacher, we use a generative LLM-based re-ranker called Lahore. It generates scores by looking at the relative log probability of specific true or false tokens within the LLM's head. This provides a very high-quality signal for the student to learn from. The student architecture inserts the predictor between the LLM layers and heads. It uses a two-layer MLP followed by a dot multiplication with the document's last embedding. Notice the efficiency. The document computation remains offline, while the online part is just slightly more than a standard biencoder, keeping the speed very high. Our distillation method is inspired by JEPA, or Joint Embedding Predictive Architecture. We use mean squared error to model the difference in latent distributions. We also use a reverse KL penalty on the log probabilities. This reverse KL is particularly helpful because it forces the student to focus on the most important peaks, the true and false tokens that define the teacher's decision. Looking at our results across datasets like ESCUNV and SACANT, RabTreaver consistently outperforms other retrievers. In fact, its performance is very close to its teacher, Lahore, while maintaining an online response time similar to much simpler models like Llama 2 Rec. In our analysis, we found that the reverse KL and the latent distribution loss are both critical for performance. From a scalability perspective, RabTreaver is much more efficient than the teacher. While the teacher's time grows quadratically with document length, RabTreaver's online time only grows linearly. It also scales well across different backbone sizes, from 0.5B to 1.5B parameters. We also wanted to see if this approach works for more traditional tasks. When tested on MS Marco and the BER benchmark, RabTreaver proved to be a strong general-purpose retriever, showing that this method of reconstructing cross-encoding is robust even for fact-based retrieval. To wrap up, rationale-based retrieval is a challenge where traditional retrievers often fail. By using our RabTreaver approach, combining a JEPA-like framework with a lightweight predictor, we can achieve the accuracy of an LLM re-ranker with the speed of a biencoder. Thank you for your time, and feel free to reach out via the contact information provided.